Hi, my name is Jeslin Thomas, and this is my video about GNSS and the moon. Imagine 50 years from now, you're on a road trip with your grandchildren on the moon, but your rover's GPS leads you the wrong way, and Pokemon Go, your grandkids' geolocation-based game, isn't working. Luckily for you, these two problems can be solved with one technology, GNSS. GNSS, or the Global Navigation Satellite System, powers location-based services on Earth, such as the Galileo system by ESA shown here. Now, scientists and engineers are working on bringing GNSS to the moon. One of these missions includes NASA's LUGA, which is currently testing lunar GNSS feasibility right now. To discuss how GNSS will work on the moon, we first need to consider how GNSS currently works on Earth. GNSS are a constellation of satellites that provide position, velocity, and time data to receivers using signals. This is done through trilateration. To demonstrate how it works, let's first look at one satellite. We can measure the distance to the receiver as somewhere on the surface of a sphere, an arbitrary distance from the receiver on Earth. Now with two satellites, the intersection of their spheres narrows down the receiver's location. Finally, with three satellites, we can see that the intersection allows us to determine that the location is one of 2 points. One of these won't be on the surface of Earth, and therefore we can assume the other to be the correct one. Now, to see how GNSS works on the moon, we will investigate the Lunar GNSS Receiver Experiment, also known as LUGA. LUGA is a NASA Italian Space Agency experiment to test GNSS on the moon using the US Global Positioning System, GPS, and the EU's Galileo. If successful, LUGA will be the first to receive GNSS signals from a lunar distance, paving the way for a connected satellite system between the moon and the Earth. Of course, an ambitious project such as this is not without its challenges. The biggest one, by far, pun intended here, is distance. Distance affects the pseudo-range equation. Pseudo, meaning not real, shows that the equation attempts to find the real position of a receiver from a satellite by also factoring in clock biases. However, with distance such as the one between the Earth and the Moon, there will be a high latency, and hence a higher error. Additionally, another geometric inaccuracy that can occur is DOP, or dilution of precision. Due to the narrow angles of the signal from the Earth satellites to LUGA, the positioning geometry will increase the location error region on the Moon. There are, on the other hand, some aspects of the LUGA mission that are better than its Earth counterpart. Firstly, there are smaller chances of multipath errors, as there are minimal vertical obstructions, like tall buildings on Earth, before it gets to LUGA. Furthermore, the vacuum of space allows there to be little to no atmospheric effects when sending signals to the Moon, removing any delays caused by the refraction of signals. Despite these challenges, LUGA remains an ambitious mission that launched aboard a Falcon 9 rocket on January 15, 2025, and will land on the Moon aboard the Firefly Aerospace's Blue Ghost lander on the 2nd of March. LUGA, alongside other technologies, will pave the way for NASA's Artemis program, intended to re-establish humans on the Moon to help facilitate crewed missions to Mars. LUGA will be a precursor for the Artemis program's LunarNet, a proposed lunar navigation and communications network. It'll provide lunar internet for future visitors of the Moon, both astronauts and space tourists. With these technologies, you can finally drive rovers and play Pokemon Go on the Moon in peace. This is the next big step in deep space navigation, helping humanity establish a presence on the Moon and beyond. Thanks, LUGA, and thank you for watching this video.